So welcome students. Today we are going to discuss red black tree insertion. Fine. So these are the outlines of the today's lecture. For the today's lecture, we will discuss first what is arbitrary. Then we will discuss how we will insert any value in the given arbitrary. Different cases may be possible. Cases 0, 1, 2, 3. So we will discuss all those ones, and then we will check the references. So after this particular lecture, you will be able to define a valid arbitrary. That means you can differentiate whether a given tree is a valid arbitrary or not. Fine. And you will be also able to insert values in a given arbitrary. So first of all, let me discuss what the arbitrary is. Arbitrary is a self-balanced tree, which was defined by the concept of the balance. This arbitrary was given by Robert Sedgwick. So he defined certain properties for the arbitrary, and those properties are, first of all, that means each and every node will have a color, either red or black. The root should be of black color. Next property is if a particular node is having red color, then its child must not be red. That means two successive nodes should not be red. Fine. So it is known as red-red conflict. Next important property which will make it a self-balanced tree is that if we are uh, traversing the complete tree, the tree from root to null node, if several paths are there, then in each and every path the number of black nodes should be equal, and that is known as the black height of the root. This property is also true for any of the intermediate node in the arbitrary. That means for any given arbitrary, balanced arbitrary, from an internal node, if we traverse through its distinct null node, that means leaf node, then in all the paths the number of black nodes should be equal. So these are the properties, and while inserting certain values in the arbitrary, if any of the property is violated, we will try to make it. Fine. So how we will make it? That is the insertion algorithm. Okay. First of all, let me discuss how we will insert a value in arbitrary. So as I want to tell you that arbitrary is following the property of BST. That means all the elements which we inserted into all arbitrary are followed the same property as the BST. That means for a particular parent node, the child must have lesser value, then it will be the left child. That means if the value is lesser than the parent, then it will be on left hand side of the parent, and if the value is equal or more than the value in parent node, then it must be on the right hand side. Fine. So before arbitrary insertion, we have to learn how we will insert in BST. So if the BST is very clear to you, that means whenever you want to insert a particular value, compare that particular value with the root, and according to whether the value is lesser or equal or greater, you have to move either in left hand side or in right hand side of the root, and you need to insert the value in the appropriate place. Fine. First thing. Second thing, whenever we inserted a value into the arbitrary, in the given arbitrary, we will declare its color as red, because as Robert Sedgwick defined, in arbitrary every node should have either red or black color. So whenever we are inserting a node, we will define its color as red. Why we are doing so, we will later on we will discuss about it. Fine. So as soon as we inserted a value and declared as its color as red, we will ask two questions. The very first question is whether the parent is existing. Fine. And the second question will be, if parent is existing, what is the color of the parent? Fine. So based on these two questions, several cases may be there. First of all, let me discuss first. If the parent is existing, its color may be either red or black. If the color is black, we will exit because there is no any red conflict. Fine. So we will exit. If the parent is existing and its color is red. So the red parent is having a red child. Earlier the parent was there which color was red, and we just inserted a new node of red color, so its color is definitely its color is red, so there is a red conflict. So we have to maintain this particular conflict, and we will proceed to maintain this we will proceed in the algorithm. If the parent is not existing, that means the answer of the first question is negative. That means the parent is not existing. Then that means whatever node we are existing, it is a root node, and as per the property, the root node should be black. So we will convert the newly inserted node's color as black, and we will exit. Now, a new item is always inserted in the leaf of the tree, as we already know that as we try to insert some value in the tree, we will compare it with the root, and as the value is less or greater or equal, we will proceed either to the left side or to the right side. If the left child is already defined, then we will again do the same thing. That means we will compare the given value to the left child or the right child, and we will proceed further to its left or its right accordingly. Right? If we inserted a node and we define its color as black, by default thumb rule is we will define its color as red. But if we define its color as black, then what will happen? In that particular branch, the arbitrary was already balanced, but as soon as we inserted a new node and defined its color as black, then in that particular branch, one new black color or one extra black color is added. So the tree will get disbalanced. So to be the tree balanced, self-balanced after the insertion, what we are doing, we will just insert a node, fine, and define its color as red. So that's why it will not disbalance the tree. Fine. Okay, next. For example, very first case, let we discuss case number 0. That means if the parent is existing and if its color is black. Fine. So here we want to insert a value 5 in the given arbitrary. So 5 is compared with 33, it is less, so we will go to left. We will compare left, already one value is existing 15. We will compare 5 with 15. We will again go to left. So in the left one value is there 10. We will compare 5 with 10, and we will again go to left, and because 10's left is not defined, so we will insert a 5 value over here. So 5 is declared as the left child of 10. We will put an arrow over it. The arrow will declare that will define that 5 is a newly inserted node, and we will define its color as red because it is a newly inserted node. Now we will ask the question whether the parent is existing. That means whether the y or the value 5 is having any parent. Yes, definitely it is having a parent which value is 10. Then we will ask the second question, what its color. The color is black, so there is no any red anomaly, so we will exit. Now second, now let me insert value 4 in the given arbitrary. Fine. So as BST we will insert, that means we will compare 4 with 11. It is less, so we will go on to the left hand side. Left hand side value is 2. We will compare 4 with 2. The 4 is greater, so we will go on the right hand side. On right value is 7. We will compare 4 with 7. 4 is less, so we will go on to the left hand side. Left hand value is 5. We will compare 4 with 5 because 4 is less, so we will go again to the left hand side, and we will insert 4 as a left child of 5. Again we will do the same thing. That means the color of 4 is red, and we will put a pointer on the newly inserted node. Again we will ask the question. We will ask whether the parent is existing. The answer will be the affirmative one. Yes, parent is existing. The value is 5. Okay, now the second question will come. The second question will ask what is the color of the parent. Now the answer is the color of the parent is red. So that's why it is a red conflict, and we have to maintain it. And to maintain this particular thing, we need to know the color of uncle. Who is uncle? So let we discuss first. In the local cluster, that means a newly inserted node, its parent its parents, which is known as grandfather, we will declare it as a grandfather, and the sibling of the parent, that means the second child of the grandfather, that is the uncle. So in our scenario, 4 is the newly inserted node, 5 is the parent, 7 is the grandparent, and 8 is the uncle. Fine. So what we will do, as soon as we will insert a value 4, declare its color as red and put a pointer over it. We will ask the very first question whether the parent is existing. Yes, the value is 5. Second question, what is the color of the parent? Okay, the color of the parent is red. That means there is a red anomaly. The red conflict is there. Now we are depending upon the uncle. So next question will be, what is the color of the uncle? Fine. Only two possibilities may be there, either black or red. If it is that means uncle's color is red, then it is known as case 1. We will try to solve it. And if the color of uncle is black, then we may either on case 2 or in case 3. Fine. So both the cases 2 and 3 are defined if the color of uncle is black. So why case 2 and case 3? We will later on check it. So now let me discuss case 1. Color of uncle is red, color of parent is red, and definitely because before insertion 4 the tree was totally balanced. Sorry. Yeah, the tree was balanced. So before inserting 4, 5 and 8 were having red color. So definitely their parents' color must not be red and it should be black. So the tree was thin. Fine. So in the local cluster, we are having 4 as newly inserted node, 5 and 8 are as parent and uncle whose color are red, and definitely the grandparents' color must be black. So the resolution of case 1 is, because we are in case 1. So what is the resolution of case 1? So the resolution of case 1 is, we will shift the color of grandparent to uncle and parent. That means uncle and parent are having common color red. This red color we will shift up. That means we will give it to the grandparent, and grandparent's black color we will shift one step down. That means we will provide to 5 and 8. What this and again, second thing, we will put this particular pointer to grandparent. Why we are doing this? Because if we make 5 and 8 black, then 5 will be a black father and 4 will be a red child. So there is, whatever the red conflict was there, it should be resolved. Very first thing. Second thing, to maintain in this particular local cluster only one black node is there, and which is on this level. So to maintain this black color as unique, what we will do, we will provide black color to 5 and 8. So on this particular label only one black color is there. Fine. On this label, please try to remember, on this particular label only one black color should be there. So 7 color should be red, 5 and 8 will have black color, and 4 is having red color. Now second thing, forcefully, initially the 7 color was black, and forcefully we are making its color as red. That's why we put this particular pointer to 7. Fine. So how we will resolve this case? This is the way. That means 5 and 8 were red, 7 was black. We will shift the color. 5 and 8 will now black and 7 color will be red, and we will put the pointer over here. Now again, because the 7 is having the pointer, so again we will ask the same question, whether the parent is existing. If parent is existing, what is the color? If parent color is not black, then what is the color of uncle? And accordingly the case 2 or 3 may be there. Fine. So let me ask the same question. We will ask this 7, okay, its color is red. Whether the parent is existing? Yes, definitely parent is existing. It is on the left hand side and the value is 2. Fine. So what is the color? Second question, what is the color of the parent? Oh, the color of the parent is red. That means there is red anomaly. Now we are depending upon the color of uncle. What is the color of uncle? The color of uncle is black. Fine. That means now we are not moving into case 1, because the case 1 is only called when the color of the uncle is also red. So here the color of uncle is black. That's why the case 1 is not called. We will call the case 2 or 3. What is the difference between case 2 and 3? Now let me define it. This is the newly pointed node. There is the parent and this one is the grandparent. We will check the position of the parent with respect to grandparent and newly pointed node with respect to parent. If parent, grandparent and newly pointed node, if newly pointed node, parent and grandparent are on left right or right left combination, that means there is a dog legged or this moved angular movement angular positioning is there, then it is the case 2. Fine. If let's suppose these three are straight, that means parent, grandparent and newly inserted node are defined either in left left or in right right position, then it is a straight one. So this is case 3. So now here we are having in our local cluster 7 is the newly pointed node, 2 is parent, 11 is grandparent and 14 is uncle. So in this local cluster what we are seeing, we are seeing that 7 is on the right hand side of 2 and 2, that means parent, is on the left hand side of grandparent. So there is left right combination. So this left right combination we have to make it left left combination. Fine. So what we will do, first of all, two things. First of all, we will shift the pointer 7 to 2, the very first thing. Second thing, we will rotate parent value, that means we will shift the pointer to the parent. Second, we will shift the parent or we will rotate the parent with respect to the pointed node. Fine. We will what rotation is needed. So it depends upon what is the relationship of the parent and pointed node. If the pointed node is on the left hand side of parent, fine, we have to perform right rotation, and if the pointed node is on right hand side of the parent, then we have to perform left rotation. So as we are having in our case 7 is on the right hand side of 2, so what rotation we will perform? We will perform left rotation. Fine. So step by step we will do. First step we will put the pointer on 2, that means on parent, and then we will rotate parent, that means node 2, with respect to 7, left rotation. Fine. So after rotation we will have a picture which will carry 11 on the left hand side, 7 and on the left hand side 2. Fine. So it will be a straight combination. A straight combination, that means case 3. So as I am defining here, if the grandparent, parent and newly pointed node, if they are in not aligned, if they are dog-legged, that means angular, then it is case 2. We will try to convert in case 3. And case 3, that means grandparent, parent and newly pointed node are in aligned condition. That means the parent, if the parent is on right hand side of the grandparent, then the newly pointed node should be on the right hand side of its parent. If the parent is on left hand side of its grandparent, then the newly pointed node should be on the left hand side of the grandparent. Fine. This is inline alignment and this is the case 3. So case 2 is there, then we will convert it into case 3 and case 3 will provide the resolution. Fine. So let in our case, in our example, 7 is newly pointed node, 2 is its parent, 7 is on right hand side of 2, but this parent is on left hand side of grandparent. So it's a angular picture. Angular picture, that means there is case 2. We will try to convert it into case 3. So how we will convert it into case 3? As I told you earlier, that we will shift the pointer on parent, first thing. In second part, we will check whether the parent and newly pointed node was, that means what was the relationship, whether they are in left, that means the newly pointed node was a left child or a right child. Accordingly, we will rotate. So in our case, 7 is a right child, so we will make left rotation. So again, 2 steps. In the very first step, we will shift the pointer to 2 and then left rotate 2 with respect to 7. So what it will be do, what it will done, it will make 7 as the parent and 2 as the left child of the 7. So this will be the picture. So 11 is on its own position, 7 is now declared as the parent, and 2 is now declared as the child, newly pointed node. That means there is red conflict still. But the thing is, grandparent, parent, and newly pointed node, they are now straight. That means they are either in left or in right combination only. In our case, in our example, they are in left combination. So let we ask the same question again and we will check accordingly. So this is the newly pointed node. We will check whether the parent is existing. The answer is yes. 7 is the parent. Okay. Second question, what is the color of the parent? Okay, the color of the parent is red. That means there is red anomaly. Now we are depending upon the color of uncle. We will ask what is the color of uncle? The color of uncle is black. That means instead of case 1, now we are going to case 2 or 3. And now we will check, sorry, what is the relationship of grandparent, parent, and pointed node? It is straight. That means we have to run case 3 only. What is the case 3? Let me show you. So in case 3, what we will do, first of all, we will recolor parent and grandparent. Recolor, or we can say we will exchange the color of grandparent and parent. That means presently 7 is the parent and it is of red color, 11 is the grandparent, it is of black color. We will shift their color. That means the color of 7 will become black and the color of 11 will become red. This is the very first step. Second step, we will rotate grandparent with respect to parent. What rotation? It depends upon how they are related. In our example, parent is 7, grandparent is 11, and 7 is on the left hand side of grandparent. So we have to maintain right rotation. Fine. So two things what we are doing. First of all, we will exchange the color of grandparent and parent. So 7 will become black and 11 will become red. First thing. Second, we will right rotate 11 with respect to 7. Fine. Second thing. Third thing, we will put the pointer on the parent node. Fine. So let me define one by one again. First of all, we will put the pointer on the parent node. So this pointer will be shifted to 7. This is the first thing. Second thing, we will exchange the color of parent and grandparent. That means 7 will become black and 11 will become red. This is second step. And in third step, we will rotate grandparent with respect to parent. In our example, we will rotate 11 with respect to 7 and it will be a right rotation. So after this rotation, this is the color change and this is the rotation. So this will be the tree. Now you can see that each and every node is balanced. Now 7 is parent, which is of black color, and 7 is having no any parent. Fine. So that means it's a root node and its color is black. First property is defined. 7 child, 2 and 11 both are of red color. Okay. 2 is red color and its 2 child 1 and 5 both are of black color. That means there is no any red conflict. And for 11, 2 children are there, 8 and 14, and both are of black color. That means there is no any red conflict. And 14 is having a right child, which is 15. Fine. And 15's color is red. So there is no any red conflict. So there is no any red conflict. Now what is the height or how the tree is balanced? Now let me check. On the very first level, that means on the root level, only one black color is there. On the second level, where 2 and 11 is there, there is no any black color. And on the third level, 1, 5, 8, 7, all are having black colors. On the next level, only 15 is having a red color. Fine. So let we discuss 7. If 7 is the root, then we are having descendant leaves, and 7 is having 4 descendant leaves. Sorry, one is 1, another is 5, another is 8, and another is 15. So For all descendant leaf, let me count 7 as a black color, so we will count it 1, and another black color is coming, then we will count it as 2. So in this particular path, that means 7 2 1, only 2 black colors are there. In the next path, and that means 7 2 5, only 2 black colors are there. In the next path, 7 11 8, only 2 black colors are there. In the next path, that means 7 11 14 and 15, only 2 black colors are there. So that means 7, if we are talking about the 7, the root node, it is having height 2. Fine, that means this particular tree is balanced. These are the references. So Poorman is the good book in which a very good example is giving. Fine. And second one is the Robert Sedgwick and Ludina's paper. Fine. This is the original work in which they defined the concept of arbitrary. And the third one is a book by Robert Sedgwick. It's a very good book, and all the algorithms are giving in C++ pseudocode. Important advice. While maintaining the balance of arbitrary, what we are doing, we are simply either rotating, that means restructuring, fine, or we are recoloring, that means define red color as black and converting black as red. So it is recoloring, and we are rotating the nodes, that means it is structuring. Fine. So these two operations are only there. So we can perform any of the operation first. That means we first, if both the operations are running, then we can first recolor and then rotate, or we can rotate first and then recolor. But advice is firstly rotate and then recolor. Fine. It will make you very clear. Fine. All the operations should be clear, but it depends upon how you can you want to run both the operations. If both the operations need to be run, you can either rotate first and then recolor, or you can recolor first and then rotate. It depends upon you. Otherwise, thank you. Thanks a lot for listening.